So our next test is the direct comparison test, often abbreviated DCT. Um, this test should sound familiar to you from the work on improper integrals, because we used a comparison test there. It was also called the direct comparison test. This basically the same concept works for series as it does for integrals. So we start by assuming that there's some integer m greater that's some positive integer m such that this inequality is true for all indices n greater than or equal to m. In other words, both sequences are positive, but 0 is less than a is less than b for all n. So if the sum from n equals m to infinity of bn converges, then so does the sum from n equals m to infinity of an, and then we sort of flip it around and say if the sum from n equals m to infinity of an diverges, then the sum from n equals m to infinity of bn also diverges. It's sort of easier to understand this graphically. So I've written here two sequences. I've depicted them as dots because, of course, they're only defined at integers like 1, 2, 3, 4, 5, like that, etc. So here what we've shown is the inequality depicted up here is true. We have an and bn are both positive sequences, but an is less than bn for all values, for all indices. So essentially what this is saying is that if the sum of bn if the sum of bn adds up to a finite number, in other words, if the sum of bn converges, then it must be the case that an does too, because an is strictly smaller than bn. So if I add up all the x's and they still come out to a finite number, then if I add up the purple dots, they should come out to a finite number as well. On the other hand, if let's suppose I add up the purple dots and they come out to infinity, since the x's are greater than the purple dots, that means that if I add up all the x's, they should also come out to infinity. So that's why these conclusions go in the direction they do. I say if bn converges, in other words, if the sum of all the x's converges, then so does the sum of all the purple dots, and then 2 is the reverse conclusion. And note, by the way, that just as we had the case with improper integrals, if the inequality goes the other way, then it doesn't work. In other words, if I were to find, let's say that an, the sum of all the purple dots, converges, I can't say anything about the sum of the red x's, because after all, if the sum of the purple dots is finite, all we can say is the sum of the red x's is greater, and there are a lot of numbers that are greater than a finite number. Some of them are finite, and some of them are just bigger finite numbers, and some of them are infinity. We don't know which one. And similarly, if we were to discover that bn diverges, in other words, that the x's add up to infinity, all we can say is that the purple dots are smaller. We don't know whether it's just a smaller version of infinity or if it's actually finite. So you have to draw the conclusions in the correct direction, and sometimes you're gonna end up with, depending on what you find out about an and bn, you may end up with an inequality from which you can draw no conclusion at all.